Welcome to the Explainer. Okay, if you've been following the AI landscape lately, it probably feels like absolute chaos, right? I mean, every single week there's a new model, some massive breakthrough, or a brand new acronym completely dominating the headlines. But what if I told you there's a hidden structure to all of this madness? Today, we are going to decode this chaotic AI landscape into a simple, elegant cheat code taxonomy. By the end of this explainer, you'll be able to look at literally any new generative model and instantly understand exactly how it works under the hood. Okay, let's dive right into this. Here is our roadmap for today. We'll kick things off with the impossible problem, then break down the 5 families, walk through 12 years of progress, equip you with the 5-question triage, talk about matching models to tasks, and finally, do a reality check on inference costs. Section 1. The impossible problem. Fighting the math. Ultimately, every generative model is really just trying to do one single job: output brand new samples from a totally unknown data distribution. But we really need to talk about the visceral nightmare of the math behind that job. Think about a single, simple 512 by 512 image. That image exists in a space of roughly 786,000 dimensions. The valid data we actually care about, the actual images of human faces or dogs, sits on an incredibly thin manifold hidden inside that massive, mind-boggling dimensional space. And, to make matters worse, we usually only have a few million examples to train on to somehow figure out where that thin manifold even is. Because of those hundreds of thousands of dimensions, trying to brute force this density is completely hopeless. You just can't do it. And that brings us to the golden rule of this entire field. Every generative model is a compromise. You simply cannot solve the math perfectly. Every single AI breakthrough you read about on Twitter is really just a calculated compromise that trades one impossible mathematical problem for a slightly less hard one. Section 2. The Blueprint. 5 AI families. And listen, if you pick the wrong bucket here, you are going to be fighting the math for weeks. And this brilliantly illustrates how the industry has essentially settled on a master blueprint to deal with this. There are 5 surviving families of compromises. 1. Explicit density that's tractable. 2. Explicit density that's approximate. 3. Implicit density. 4. Score-based or continuous time models. And 5. Token-based autoregressive models. Every single model making headlines right now, from ChatGPT to Sora, fits perfectly into just one of these 5 buckets. Now, if you read the papers, you're going to hear the terms explicit and implicit density constantly. So what does that actually mean? Well, think of it like this. Explicit means the model actually does the math. It provides a tractable log probability that you can evaluate to see exactly how likely a specific data point is. Implicit density, on the other hand, is basically a GAN-style sampler. It generates a sample for sure, but it gives you absolutely no way to evaluate the mathematical probability of that specific point. It basically just guesses and checks. Let's look closer at the first 2 families. Family 1 includes autoregressive models and normalizing flows. These are explicit and tractable. They give you the exact likelihood, which is fantastic. But the compromise is that they are sequentially very slow, or they force you into really restrictive architectures. Then we have Family 2, which includes VAEs and your standard diffusion models. Their compromise? They totally give up on exact math, and instead they optimize an approximate lower bound, which we call the ELB. So, moving on to Families 3 and 4, the math gets handled quite differently. Family 3 are the GANs. They say, you know what? Let's skip density estimation entirely. That makes them blazingly fast, but notoriously unstable and finicky to train. Then we have Family 4, which is absolutely the massive 2024 to 2026 hotness: flow matching and score-based models. Instead of guessing, they learn the gradient of the log density directly. This gives them these incredibly straight, efficient paths for generation, making sampling like 4 to 10 times faster than standard diffusion. And finally, we have Family 5, token-based autoregressive. Honestly, think of this as just taking Family 1 and slapping a learned tokenizer onto it. The strategy here is to compress high-dimensional data, like, say, an entire video, down into a short sequence of discrete codes or tokens. Once it's compressed, you just unleash a standard, highly optimized transformer on it. This brilliant little compromise, that's exactly the secret behind Sora's highly publicized patch tokenizer. Section 3. 12 years of progress. The evolution. Let's see how the industry aggressively jumped between these 5 buckets as compute power scaled up over the last decade. Let's move to the timeline and see how this builds, because it's super fascinating. In 2013, VAEs gave us the very first usable training loss. Then, bam, 2014 hits and GANs explode onto the scene with these incredibly sharp implicit density samples. Fast forward to 2020, DDPM finally makes diffusion practical. By 2022, latent diffusion is completely dominating text to image. In 2024, flow matching swoops in to win the video generation race. And now, here we are in 2026, and the holy grail is finally upon us, using consistency and rectified flow for one-step sampling straight from those diffusion backbones. Section 4. The 5-question triage, a practical playbook. Now let's talk about how you evaluate all this stuff in the wild. I highly recommend you reflexively ask yourself these exact 5 questions before you even glance at the method section of whatever new paper drops tomorrow. First, what exactly is being modeled? Are we talking pixels, latents, or discrete tokens? Second, is the density explicit or implicit? Third, is the sampling iterative, meaning slow, or is it one-shot? Fourth, what is the conditioning guiding the output? And fifth, what evaluation metric are they actually using? Seriously, answering these 5 questions instantly cuts right through the marketing hype. Section 5. Matching models to tasks in 2026. Let's talk about what you should actually be deploying. Now, what's really interesting about this slide is that the newest tech doesn't automatically win across the board. If you're building a product today and you need a narrow domain, like photorealistic faces, Style GAN, an older Family 3 architecture, is still absolutely the best choice because its inference is just blisteringly fast. But if you need general text-to-image, latent diffusion paired with flow matching definitely takes the crown. And text-to-video, that space is completely dominated right now by diffusion transformers coupled with flow matching. Section 6, the reality check, translating faster into inference costs. This brings us to a massive production reality check. Marketing claims about a model being faster in some abstract academic sense, totally meaningless unless you ruthlessly translate them into actual server compute costs. For autoregressive models, you are going to suffer from brutal sequential latency. The decode time completely dominates your cost. Now, for VAEs, diffusion, and flow models, you don't have that LLM-style decode. Instead, your cost is literally just the number of steps multiplied by the compute cost of one step. But a GAN gives you a blistering single forward pass. The total latency is practically instantaneous. And that brings us right back full circle. As we keep watching this incredibly fast-moving space, I want to leave you with one key thought. The next time a massive breakthrough AI paper drops and literally everyone is hyping up its capabilities, don't just look at the shiny results. Remember that impossible 786,000 dimensional problem? Look closely and ask yourself, what hidden mathematical compromise did they actually have to make to pull this off? Because trust me, in generative AI, there is always a trade-off. Thanks for joining me on this explainer. Keep asking the hard questions, and I'll catch you next time.